Welcome to the ChemDoctor, and the purpose of this video is to provide my viewers with more practice in regard to limiting reactants and theoretical yields. So let me lay down the framework for this. Let's say that we had a reaction between sodium metal and bromine to produce sodium bromide. And let's just say, for the sake of argument, that I'm going to combine 1.8 moles of sodium metal with 1.4 moles of bromine, and I want to calculate the theoretical yield of sodium bromide. Now, what I want to deal with first here is the concept of the limiting reactant. You can see that we've been given quantitative amounts of both reactants. And when you look at the balanced equation, you can see that there's a coefficient of 2 in front of the sodium, a coefficient of 1 in front of the bromine, and a coefficient of 2 in front of the sodium bromide. What this means is that for this reaction to take place, we need a ratio of 2 sodiums to 1 bromine in order to form 2 sodium bromides. All right, and we've been given moles of both the sodium and the bromine. The problem is, when we're given quantities like this for a chemical reaction, more than likely one of the two reactants is in short supply by comparison to the coefficients in the balanced equation, meaning that in this particular combination we need a ratio of 2 sodiums to 1 bromine. So we need to be able to look at these two quantities that we've been given, that we're actually inputting into the reaction, and determining which of the two reactants is in short supply. Because whichever of the two reactants is in short supply, that reactant is going to run out before the other one, controlling the theoretical yield of the reaction. Remember that the theoretical yield of the reaction is the maximum amount of product that we can form in this reaction if the reaction is allowed to go to 100%. But the maximum amount of this product that can form is going to be dependent on whichever one of these two reactants is the one that is present in short supply, because it is going to run out before the other reactant. Now, before we get into the nitty-gritty of this, because I realize that this is a fairly complex idea, let's forget the chemistry for a minute and go to a simple real-world example. All right, let's say it's my job to build cars. All right, and this is a completed car body. It's got everything that you need to run this car except for tires. And I'm going to set up a simple chemical reaction where we're going to assume we have 1 mole of car bodies. Again, this has got everything in the car that we need to run a car except for tires. The last step on the assembly line is to put the tires on the car. Now, common sense tells us that you're going to need 4 tires per car body to complete this car. And here's my reaction arrow. So what this arrow means is, if we have 1 car body plus 4 tires, that will produce, that's what the arrow means, will produce a completed car. So let's get the picture of that over here. All right, and this is the completed, I'm just going to abbreviate that, completed car. All right. And the coefficient here is 1. So we see the ratio of car body to tires is going to be 1 to 4. We need 4 tires for every car body to produce 1 completed car. All right, now let's look at this from a limiting reactant point of view of chemistry. So let's say that I have exactly 2 car bodies that have been provided to complete the assembly process, and I have a total of 7 tires left in the pile on the warehouse floor. You can see there's a problem here, because since we have 2 car bodies and 7 tires, that's not enough tires to complete all of the cars. And in fact, the best we're going to be able to do here is to produce one car and 3/4 of another. All right. The bottom line is though from the point of view of the assembly line, the best we're going to be able to do in this reaction for a theoretical yield is going to be the production of one car, because there's not enough tires to complete the other car. So saying that we've got 3/4 of a car left is meaningless, because this car is not usable. This car is going to sit in an uncompleted form on the warehouse floor until the right amount of tires shows up. All right, now let's see how we can use unit multiplier method to solve the theoretical yield the same way. So before I do that, just to reiterate, my theoretical yield here is going to be 1, because one complete car is all I can get out of the assembly line, given two car bodies and a total of 7 tires. Now let's see how we can use unit multiplier method to solve the same problem. So what I'm going to do is I'm going to pull down my information. So I've been given 2 car bodies. All right, and I have a total of 7 tires. Now we're going to go ahead and calculate the theoretical yield of completed cars using each reactant as if the other reactant is in excess. Or you can look at it this way if you want. We're going to calculate the theoretical yield of completed cars using each reactant as if the other reactant doesn't exist. Even though that we know that we need it, we're going to pretend, we're going to ignore the fact of the tires in one case, and we're going to ignore the fact of the number of car bodies in the other. And we're going to go ahead and use each quantity that we've been given as an independent value, and we're going to calculate the maximum theoretical yield that we could get. So in the numerator of this fraction, I'm going to write down what it is we're solving for. One complete car here and one complete car here. Now, in terms of the car bodies, what I want to relate is the coefficient for the completed car to the coefficient of the car body. And we see that the coefficients are 1 to 1. So in order to cancel car body, this value is going to be over 1. I need the coefficient that is in front of car body. And then I'm going to write down the correct label. All right, and in the case of the tires, all right, I'm going to write a 4 for that. That's the coefficient. And then what it is I want canceled. What it is I want canceled. All right, and now let's take a look at this. We see for the top equation, car bodies cancels with car bodies. And 2 times 1 over 1 is simply 2. So if we had an excess of tires, the maximum amount of completed car, whoops, I want to be more explicit about this, sorry about that, very quickly. All right, so we're going to have 2 moles maximum of completed car that we could form if we had an excess of tires. And in the other case, we see the tires cancels out, and in this case, 7 divided by 4, we see that the 4 is going to go into the 7 one time, and then there's going to be 3 tires left over to make 3/4. So the most moles of completed car that we can get here is going to be, as I stated above, the best we're going to be able to do is get 1 completed car out of this. So that makes the tires the limiting reactant. All right, now if we go back to our chemical equation where we have moles provided of both the sodium and the bromine, all right, let's go to another screen now. So let me rewrite my equation. I've got 2 sodiums plus 1 bromine to make 2 sodium bromides. All right, and I've been given 1.8 moles of the sodium and 1.4 moles of the bromine, and my theoretical yield is going to be the sodium bromide. So using the same technique as I showed in the previous slide with the cars, I'm going to pull down my information. So I've got 1.8 moles of sodium, and I have 1.4 moles of the bromine. And what we're going to do is calculate the theoretical yield of sodium bromide using both reactants as if the other reactant is in excess. So we're going to be solving for mole of NaBr using both reactants independent of the other reactant. All right, so this is the challenge. All right, and then once we've calculated the moles of the NaBr, we simply just compare the two numbers, and whichever number is smaller, that is the value that had to come from the limiting reactant. So let's go ahead and take a closer look at this. So what we want to solve for is the NaBr, so I'm going to pull its coefficient down into the top of the numerator or the fraction for both fractions, because we're solving for the same thing in both cases. All right, and then we want, in the case of the sodium, we need to cancel the sodium and solve for the NaBr. So we're going to retrieve the coefficient for the sodium, and that goes into the bottom of this fraction here. And for the bromine, we need its coefficient, so I'm going to pull down the 1. I think I can sneak through here. And it goes right here. So we have 1 Br2 that goes here. Now let's go ahead and deal with the math. So we have 1.8 moles of Na times 2 over 2. So I think the viewer can see that this 2 is going to cancel with this one. The fraction is going to be equal to 1. So the maximum NaBr we could make using this reactant is going to be 1.8 mole of NaBr. All right. In the other case, it's going to be 1.4 times 2 over 1. So we're going to end up with 2.8 moles of NaBr in this case. So now to determine the limiting reactant, we compare these two numbers. And you can see that the 1.8 is smaller than the 2.8. So I'm going to come back over here and circle this now. The sodium is the limiting reactant. It's the thing, it's the reactant that is going to run out before the other, and it's going to control the theoretical yield of the reaction. So the most NaBr that we can make in this reaction will be 1.8 moles. All right, and with that, I'm going to go ahead and close the video. I would like to thank the viewer for watching, and you can find more videos at www.chemdoctor.org. Thanks again for watching, and hope to see you again.